Okay. So, the study of the visual cortex, okay, this area is called neocognitron, okay, neocognitron. And this name, okay, was introduced in 1980s, which gradually evolved into the convolutional neural networks, okay. So, important milestone was a 1998 paper by Yang LeChong, Leon Batu, Joshua Benjo, and Patrick Hafner. Okay, you see the first author is Yang LeChong. Okay, in this paper they introduced a famous LaNet 5 architecture. This LaNet 5 architecture, what does it do? It recognizes handwritten digits. Okay, and this is considered to be the first CNN architecture. Okay, it has several building blocks that even now we are use those building blocks in our CNN neural networks. Okay, I mean the two most important building blocks: convolutional layers and the pooling layers. Okay, so I think today we probably can only cover convolutional layer. Okay, we will cover pooling layer next time. I'm not sure if I'm able to finish convolutional layer today. Okay, and also remember I told you we are going to review several important CNN architecture. LaNet 5 is also one of them. Okay, but I don't think we can talk about that today anyway. Okay, so you may wonder, why don't we just use a regular deep neural network with fully connected layer for image recognition test? Okay, well, actually this approach works fine for small image. For example, handwritten digits, MNIST. Okay, we could use like a fully connected layer, okay, to recognize handwritten digits. Okay, it's a 28 by 28 resolution. It's very small. Okay, but when image become large, this approach has an issue, because remember, in the MNIST data set, we treat those 28 by 28 into like a 784, right? 784 different features, right? We basically flatten those two-dimensional image into like a one-dimensional features, right? We have 784 features. Okay, so for like a fully connected layer to deal with 784 features, okay, even with two additional deep, dense layers, it's still fine. Okay, but when the image size, for example, becomes like large, such as like a 100 times 100 image. Well, this is actually a very small image, to be honest. Like, when you take a photo by your smartphone, okay, any image you get from your smartphone, it's going to be, much larger resolution, right? Much higher resolution than this 100 by 100. So just 100 by 100, then you are going to have like 10,000 pixels. If the first layer is 1,000 neuron, then this means a total of 10 million connections. So that's just the first layer. If you have like another few layers, then CNN, then it's going to be too much to store in the memory. Okay, so CNN solved this problem using partially connected layers and weight sharing. We are going to get to this later. Okay, in CNN, it's not fully connected. The layers are not fully connected. So you don't have this many, number of weights to deal with. Of course, because the input after all is like a higher resolution. So yeah, I mean, in CNN it's still very easy to run out of memory. Okay, but you know, if CNN can run out of memory, I mean, obviously DNN cannot do it. Okay, DNN requires much more memory. Okay, so let's first look at the first building block of the CNN. Okay, which is the convolutional layer. Okay, so neuron in the first convolutional layer are not connected to every single pixel in the input image, because remember in the input layer in the DNN, okay, the first hidden layer, the neuron in the first hidden layer, it actually receives the input from every input neurons, right? But now for the CNN, okay, for the convolutional layer, okay, for the first convolutional layer, the neuron are not connected to every single pixel in the input image. Okay, so the concept is kind of like what happens? Yeah, the concept is kind of like here. Okay, it is only connected to, well, I probably should point to this. This is only connected to like a small range input. Okay, so it's something like this. So, yeah, but only 2 pixels in their receptive fields. Okay, so in turn, each neuron in the second convolutional layer is connected only to neurons located within a small rectangle in the first layer, and so on. So, so you may ask, wait. In the previous picture that I show you, okay, here we use circle, right? We use circle to indicate different receptive field, right? So you may wonder, why not circle? I mean, because I just told you it's a rectangle, right? Small rectangle. So why rectangle? Why not circle? Because if it's a circle, then circle require like more computations, right? If it's a rectangle, you just need to know the width and the height and width, and you know like where you are, right? Okay, because here, okay, we want to be able to compute faster. So rectangle is much easier to deal with than circle. Okay? So this architecture allows the network to concentrate on low-level features in the first hidden layer, then assemble them into higher-level features, okay, in the next hidden layer, and so on. Okay, so this hierarchical structure is common in real-world images, which is one of the reasons why CNN work so well for image recognition. So you can see this idea is kind of similar to this one. The only difference is that here, okay, each receptive field is circle, but here in here, okay, each receptive field is actually a rectangle. Okay. So all the multi-layer neural networks we have looked at so far had layers composed of a long line of neurons. Okay, so we have to flatten input image into one-dimensional before we feed them to the neural networks. Okay, but in the CNN, each layer is normally represented in 2 dimensions. Okay, as you can see here. Okay, each layer is represented in 2 dimensions. It's not like we cannot deal with like any input. I mean, that is not 2D. Okay, actually we could deal with more, for example, 1-dimensional input. In CNN, we can deal with even like a 3-dimensional input in CNN. But But, okay, for ease of understanding, we will discuss 2D CNN first. Okay, later on we are going to talk about 1D CNN. Okay? So, which makes it easier to match neurons with their corresponding inputs. So a neural net located in row I, column J of a given layer is connected to the outputs of the neurons in the previous layer located in row I to I plus FH minus 1. So, and the column J to J plus FW minus 1. This FH and FW are the height, indicate the height and the width of the receptive field. Okay? Again. So this is this size indicate the FH. This size indicate the FW. Okay? So basically, something like this. Okay? So in order for a layer to have the same height and width as the previous layer, it is common to add zeros around the input as shown in the diagram. Okay? This is called zero padding, something like this here. In this example, you can see the FH and the FW are both 3. So I mean, each time we get this area, this neuron is you know basically you know connected to this area. This neuron is connected to this area, and so on. 3 by 3. Okay, and this gray area. I mean, this is the original input. Okay, this is the original input. The gray area indicates like the area that we pad the zeros. Okay, because if you look at here, okay, because this one has 3 by 3. This one has 3 by 3. I mean, with moving one to the right. Okay, this one has 3 by 3, moving to the right, and so on. So eventually, you will see that. Okay, yeah, I mean, it doesn't match because obviously we need a bigger input in order for these two to match together. So, but if you don't want to increase the input, I mean, we do the zero padding. Okay, so first, I mean, each of these neurons is connected to these 9 locations. Okay, and then it's also possible to connect larger input layer to a much smaller layer by spacing out the receptive field. Okay, so for example, like here, the previous one, you can see these two, the size of this area and the size of this area is the same. That's why, okay, when each neuron is mapped to a, I mean, area larger than maybe 2 by 2, I mean, we will have to, you know, have zero paddings. But I mean, in this example, you can see this area and this area, they are different. This one is much smaller than this one, right? Okay, so what do we do? Okay, you can see we still use zero padding here, but from here you can see this one is in charge of this 3 by 3. But this one, when we move one position to the right, we actually move two positions to the right in the lower layer, right? And so on. Okay, so here, okay, in this case, okay, this distance between two consecutive receptive fields is called stride. This stride. Okay, so the example here, okay, because we are moving 2 units to the right, okay, for the consecutive receptive field. So the stride, okay, for the width is 2. The stride for the width. And be careful. Stride also has height and width. Okay, because stride also has 2 dimensions. Okay, so SW in this case is 2. I mean here, okay, the stride for height, I mean, is 2 too. Okay, so you can see this one is mapped to this area. Okay, because we have to move 2 unit up. Okay, for this one. Okay, so so 5 to 7 input layer is connected to a 3x4 layer. Okay, using 3x3 receptive field and a stride of 2 on both directions, on the horizontal and the vertical direction. Okay, so but be careful, okay, because the stride could be different on 2 different directions. Okay, but to be honest, even I say the stride could be different on the width and the height, but actually most of the case, you will see the strides for width and height are said to be the same value. Okay, so a neuron located in row I, column J, in the upper layer is now connected to the outputs of the neurons in the previous layer located in row I times SH to I times SH plus FH minus 1. Columns J plus SW to J times SW plus JW minus 1. So the width and the height of the receptive field is still FH and FW, but now because each time you move SW, so now you have to move, a little bit further. Okay. So you can see that, okay, in order for one neuron to find out its own connection to the lower layer, okay, using this rectangle way, it's much easier to compute, right? Because you just need to know the range. The index, is within a range, okay, and then that's your the neurons that you in the next layer for you, okay. So this is why the receptive field is said to be rectangle, okay. So a neuron's weight can be represented as a small image, the size of the receptive field, okay. For example, the figure in the slide number 16 shows 2 possible sets of weights called filter. Okay, so the first one is represented as a black square with a vertical wide line, okay, in the middle. So it's 7 by 7, full of 0, except for the center column, which is full of 1. Okay, so it's before I show you the example, I just want to tell you what exactly we are talking about here. Okay. Remember I told you this neuron is connected to these 9 locations, right? Right? But eventually, okay, we know this one gets input from this 9 location, but how does the input get computed? Okay. We are going to get the weighted sum. Okay, so we are going to have a filter. Remember, this is the receptive field is 3 by 3, right? So filter is of size 3 by 3. So filter is 3 by 3. So it's okay. So for example, 1 0 0 0 1 0 0 0 1. So this is one possible filter. I'm not saying this is the only filter. Okay, so this is a 3 by 3 filter, and it tells you that, okay, so this is you multiply this one to the corresponding location here. Okay, for example, this one, okay, when you multiply with this one, you are going to get this value plus this value plus this value, the diagonal one. The others, because they are all zeros, right? This is 0, this is 0, this is 0, this is 0, this is 0. The other ones, because they are all 0. So when you multiply the other value to those filter, they all become 0. So you are going to multiply, when you multiply this area to the filter, what you get is the sum of this diagonal, and then you are going to put that value here. Okay, so this is filter. This is filter. it's obvious it's 3 by 3. Okay? And this filter, first, this filter is going to be reused. It's going to be reused. Here, we use this filter to calculate this value, right? So we are going to use the same filter to calculate this value, but this time from this area. Okay? And then from this area and so on. Okay? So the same filter gets used to calculate all the values here, but from different locations. Okay? So, so this is the idea of the filter. But you may say, so how do we know what value we should put for each of this value, each of the space here in the filter? The filter, the values in the filter are not decided by you. It's learnable. It's when you train the CNN, the most important job is to determine the value in your filters. Okay? So even though here we write it's 100010001, because this is an example, I just want to show you the function of a filter. So I give a value for this filter, but eventually when you train the CNN model, the filter does not have a predetermined value. It's the filter value are learned from the training. Okay? So, so you may ask, what is this? This show you this one. Okay? So this is the input picture. I think because we are, we Eastern culture knows about this, right? This is temple, right? Okay, everybody knows about this picture, right? Okay, so if you have this filter, this is a 7 by 7 filter. Okay, 7 by 7 filter. Every point is 0, except the central vertical line is 1. So every other location will be 0. Okay, except the central. So it's and when you apply this vertical filter to this picture, what happens? You are going to get something like this. When you apply a filter like this, which is like all 0 except the middle horizontal line. The middle horizontal line is all 1. Okay, and all the other positions in this filter are 0. If you apply this horizontal filter to this picture, this is what you are going to get. Okay? So you may wonder, well, so I understand this picture, but I don't understand the top two. The top two looks blurry to me, right? It doesn't show anything. But one important fact you can observe, the left one, okay, after you apply the vertical filter, the vertical features get enhanced, right? Because, for example, these are the what should I say? Okay, how to say that in English? Okay, basically you have a couple of this structure, right? Horizontal structure, vertical structure, right? In the building, and when you apply this vertical filter, this vertical structure gets enhanced, obviously, right? Okay, and of course this temple also has some horizontal, because for example, this part is a roof, right? Rooftop. This part is the inside house, but between these two there is a horizontal line to separate them, right? And this horizontal line, after you apply this horizontal filter, you see this line, this separation gets enhanced, right? Okay, so it actually helps you to, what should I say, like enhance certain features. Okay, it helps you to enhance certain features. So of course, like depending on your filter, okay, I mean the feature that gets enhanced will be different. Okay, and each one, okay, each one after you apply one filter, you are going to get the image you are going to get. We call that feature map. Feature map. So for this input, okay, with this filter you get this one. With this filter you get that one, right? So each of these two is called a feature map. Okay, so each filter will give you one feature map. Okay, and in one convolutional layer, it is very common to have a lot of filters. 32, 128, that's very common. So eventually, you are actually going to have not one, but many layers, okay, formed by all these feature maps that are, the result of different filters, okay? So, these feature maps are stacking up one by one. So, in reality, okay, if this is your input, okay, after you apply one convolutional layer, you are going to get a lot of feature maps, something like this. And each layer is a result of one filter. Okay? So this is convolutional layer 1 and the convolutional layer 2 and so on. Just want you to get an idea. And you may wonder, wait. How come the input is something like this? Shouldn't we just have like one input? Because normally, if the input is an image, okay, unless it's a grayscale, okay, then if it's a grayscale, normally it's just one layer. But if it's like a colored image, okay, we normally treat it as a RGB. We'll treat the input into 3 different channels. Okay, one represent R, one represent green, one represent blue. Okay, RGB. And you may ask, so these are called channels. Okay, and you may ask, like, can we have more than 3 channels? Yes, sometimes we could. For example, remember, like, next to our building, we have like a remote sensing, right? Remote sensing center, right? And they have satellite, right? The image obtained by the satellite actually has a much wider spectrum. Okay, and they will probably chop the for each different range of spectrum, it's considered one channel. So you can have, like, for example, like infrared channel, and then RGB, and then like ultra something. Yeah. But anyway, just like you can chop the spectrum into different channels. So you could have like more than 3. Okay? Just want you to understand that. Okay? So and also the fact that all neurons in a feature map share the same parameters. Okay, this same parameter means like same parameters in a feature map. In the filter. Okay, dramatically reduces the number of parameters in a model. But most importantly, it means that once CNN has learned to recognize a pattern in one location, it can recognize the same pattern in any other location, because you are going to use the same filter for for the same for the whole feature map anyway, right? So in contrast, once a regular DNN, like a regular DNN, has learned to recognize a pattern in one location, it can only recognize that pattern in that particular location only. So CNN is able to be able to learn the pattern which is independent to the location, which is important concept. Okay. So I already talked about color channel. Okay. So input image are also composed of multiple sublayers, one per color channel. Okay. So I already talked about this. So specifically, because now we have not only the width, the height, the stride, but also the layers, right? The layers, because the feature map has multiple layers. So so a neuron located in row I, column J of the feature map K in a given convolutional layer L, okay, is connected to the output of the neurons in the previous layer L-1, located in row I times SW to row I times SW plus JW minus 1, and the columns J times SH to J times SH minus FH plus FH minus 1 across all feature map. Be very careful. Across all feature maps. Okay? In layer L-1, okay, it is going to go across all feature maps. Okay? So know that all neurons located in the same row I and the column J but in different feature maps are connected to the output of the exact same neurons in the previous layer. So this is very important. Okay? So we could, okay, write it mathematically, something like this, okay, just by equation. Okay, the Zijk, okay, is a result of BK. BK is a bias, plus, okay, this this represent the column, this the row. This represent the column. This represent different feature maps, okay, and it's X I prime J prime K prime times WUV K prime K. This is the way this W is actually from the filter, okay, and yeah. So we try to summarize what we are talking about here by an equation here. Okay, so that's pretty much, I mean, well, sorry, very straightforward. Okay, actually, if you write it in mathematically, in an equation, it's much easier to understand. If you are not so afraid of math, this is much more elegant actually. Okay, so in TensorFlow, each input image is typically represented as a 3D tensor of shape, height, width, channel. Okay, why is it 3D? Now you get an idea. Remember we talked about max known regularization. I told you that it's like the CN has 3 dimensions. So now it's a height, width, and the channels. So mini batch is represented as a 4D tensor. Mini batch, size, height, width, channel. So the weights of a convolutional layer are represented in a 4D tensor, something like this. So the bias term of a convolutional layer are simply represented as a 1D tensor of shape Fn. Okay, so we can look at a simple example. The following code loads 2 sample image using scikit-learn load sample image. Okay, well, one is Chinese temple, the other one is a flower. Okay, and we create 2 filters and apply them to both image, and finally it plots these two images, the result. After applying the filter, so it's something like this. Okay. Here, so China just low sample image. Okay, this is China JPEG, and we divide it by 255 so that each pixel is now in the range of 0 to 1. Okay, and by the way, these two images are grayscale, so it only has one channel. Okay, it only has one channel. So flower, again, we divided by 255. So each pixel is between 0 to 1. And then, okay, we put them together into an image. Okay, and then we put them into this shape. Okay, batch size, height, width, channels. Okay, in which channel is 1, obviously, because it's a grayscale. And the batch size is 2. And the height, width, it's that's it. So create two filters. So here, okay, filter equal to NP zeros. So we try to create a 7x7 filter, okay, and fill in zeros for all of them. And for the first filter, we fill in like 1 to the center vertical line. The second filter, we fill in the center horizontal line to be 1. So actually, we are creating exactly this one. It's just we have a Chinese temple and another flower, but the flower is not shown here. But we create a vertical filter, horizontal filter, just like this. Okay, and then, okay, see, we apply these filters to the images, okay, by using the TensorFlow's Conv2D. This is TensorFlow version, okay. Later on, we are going to talk about Keras convolutional layer, okay, which is also obviously also Conv2D, but with a different, prefix, okay. So after applying these filters with padding same just equals same just means like we add like 0 paddings. We add 0 paddings, okay, when we apply the filters, okay. And then the image that we are getting, okay, are stored in output. And then, okay, here, okay, we try to, put them, output these images, okay, and by using these two lines. And result is actually not only these two, but also the other two images from the flower, but it's not shown here, but you get an idea, okay? So this is just an example, but the explanation I think I already explained, okay? So, so padding must be either same or valid, okay? If it's same, okay, then the convolutional layer use 0 padding, as I said, if necessary, okay? The output size is set to the number of input neurons divided by the stride, okay, rounded up. So if the size is 13 and the stride is 5, then the output size is 3, okay. Basically, like because 13 divided by 5, round up, is going to be 3, okay. But if it's 3, then obviously you need to pad something, on the side, in order to make it. So zeros are added as evenly as possible around the input, okay, as necessary. So it's something like this, okay. Here, okay, because the stride is 5, right? So the first one is like here, okay. We use this 1, 2, 3, 4, 5, 6, and then move 5 position to the right. Okay, 1, 2, 3, 4, 5, 6, and then again move 5 position to the right. So starting from here, 1, 2, 3, 4, 5. Yeah. So you can see that, okay, we do need to add 3 zeros. 3 zeros. But we don't add 3 zeros only on one side. We try to add it on 2 sides as evenly as possible. By the way, this is a one-dimensional example, right? Okay, but you get the idea. It can be used for 2-dimensional, obviously. Okay, and this is the case when we set the padding to be the same. Okay, to be same. You could also set the padding to be valid. If you set the padding to be valid, okay, then and because each one is requires 6 input, right? So the whole input is 13, right? And 13 divided by 5, right? 5 or 6. Yeah, 13 divided by 5 is 2.6. Then we pretty much, drop the rest. For example, starting from here, 1, 2, 3, 4, 5. Okay, and then we move like to here, and then 1, 2, 3, 4, 5, 6. Okay, sorry, 1, 2, 3. Yeah, the stride is 5, so we move to here, and then 1, 2, 3, 4, 5, 6, and then we still have 2 right here, right? But because we set the padding to be valid, so we will, even though we have some unused input, so we will just ignore them. We just drop them. But the drop only happen at the end. It doesn't happen. We don't evenly distribute it in these drops. Okay. So this is slightly different. Okay. The padding, the 0 padding, is done on both ends as evenly as possible. But drop only happen at one side. Okay. Just want you to be aware of that. Okay. So, I think I explained this already. So, okay. So filters are trainable in real CNN. In the example I just showed you, okay, we set the filter. For example, we set like these 2 filters. This filter and this filter manually, right? We set this filter and this filter manually. And I also give you this filter and set this filter kind of manually, right? But in reality, when you have a CNN, okay, when you create a convolutional layer, the filters are trainable. Okay, the filters are trainable. What happens? Okay, filters are trainable. So for example, here, okay, and you have a lot of filters actually. So here, okay, for example, if you want to use Keras to create a convolutional layer, it's going to be something like keras.layers.conv2d. You see, filters equal to 32. So you create 32 filters. Kernel size equal to 3. It means each filter is of size 3 by 3. Okay, 3 by 3. Stride equal to 1. Okay, that means the vertical and the horizontal strides are both 1. As I said, okay, a lot of time, the vertical and the horizontal strides are the same. Okay, a lot of time. Okay, and the padding is the same. Activation is ReLU. So actually, okay, we haven't talked about activation function yet. Actually, remember this formula? Once we add this together to be this value, we have to apply activation function on this value. Okay, on that value, and then to be the output of that neuron. Okay? So, okay, so this code creates a conv2d layer with 32 filters, each 3 by 3. But here, okay, the values in these 32 filters are not decided. It will be decided during training, okay, by backpropagation. Okay? So using a stride of blah, 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 I think the other are sort of like trivial, okay? So I think like, let me finish this slide, okay? So another problem with here is that the convolutional layers require a huge amount of RAM, especially during training, because the reverse path of backpropagation require all the intermediate values computed during the forward pass to be stored. Okay, so for example, consider a convolutional layer with 5x5 filter, outputting 200 feature maps. Okay, feature maps of size 150 by 100, with stride 1 and the same padding. Okay, so if the input is 150 times 100 RGB image, this is not large, right? Not big. The resolution is reasonable, 150 by 100, right? But it's RGB, it's a color image, which is also not surprising. Okay, so the number of parameters is actually 5 times 5 times 3 plus 1, because for each this 5 times 5 is from the size of filter, times 3 because we need the filter. We have 3 channels. Okay, each channel has a different value. Okay, in the filter. Okay, so 5 times 5 times 3 plus 1. Why do we have this plus 1? Because this 1 is the bias. It's a bias. Okay, and remember we have 200. We have 200 feature maps. That means we have 200 of such filters, right? So each filter has this many parameters. Okay, so we need to multiply this by 200. So we have, 15,200, parameters. Okay, parameters. So which is very small compared to a fully connected layer. Okay. However, each of these 200 feature maps contains this many neurons, right? So and each of these neurons needs to compute the weighted sum of this 5 by 5 by 3, 75 input. So that's a total of 225 million float multiplications. Okay, a lot of multiplications. Okay, and not as bad as fully connected layer. Okay, still much better, but still quite computational intensive. Okay, it's already going to take some time. Okay, moreover, if the feature maps are represented using 32-bit floats, then the convolutional layer output will occupy 200. 200 is the number of feature maps, right? By 150 by 100, this is the size of each feature map. By 32, 32 is the number of bits required for each pixel, right? So it's going to be 96 million bits, about 12 megabytes of RAM. Okay, that's still not too bad, right? But it's just for one instance. Normally, when you train a model, you are going with a batch, right? If each batch, okay, has 100 instances, again, 100 instances for one batch is not too much, right? It's reasonable, right? Of course, Yang LeChong suggests you 32, but 100 is still not too far away from the suggested value. So each instance is 12 megabytes. So 100 is going to be 1.2 gigabyte of memory. So so this is quite a lot, right? This is quite a lot of memory requirement. So you can see that when you train an CNN, it is very easy to run out of memory. So it is also very important that your GPU card to have enough memory to train a CNN model. Okay, because just this small example, need like 1.2 gigabyte of memory. Of course, this is nothing. Okay, compared with like a fully connected layer, because a fully connected layer with this many neurons, each connected to 150 times 100 times 3. This 3 is a channel, right? This many inputs would have this much, okay, parameters. So this is 675 million parameters. Originally, here, how many parameters are we talking about? We are only talking about like, for this layer, it's only 15,000 compared with like 675 million. You see, they are totally different scale, right? Okay, that is why CNN save a lot of memory compared with a fully connected layer. But even for the CNN, it is still going to, a lot of times it's going to run into trouble with the memory. Yeah, it's just because, well, the image takes space. Okay? So the remedy, okay, during inference, okay, so the RAM occupied by one layer can be released as soon as the next layer has been computed. So you only need as much memory as required by 2 consecutive layers. But during training, everything computed during the forward pass need to be preserved for the reverse pass. So the amount of RAM needed is the total amount of RAM, okay, required by all layers. Well, remember that 1.2 gigabyte is only for one layer. So if you have 10 layers, it's 12 gigabyte. Okay? So this quickly add up. Okay? So if training crashes because of out of memory error, you can try reducing the mean batch size, because as I say, the batch size matters, right? The 100, if 100 is too big, try 32. Okay, you have like you cut like roughly like a 2/3 of memory usage. Okay, alternatively, you can try reducing dimensionality using the stride. Okay, or removing few layers, or you can try using 16-bit float instead of 32-bit float. Because each pixel, if you use 32-bit float and you try to reduce it to 16 bits, then you cut the model and everything by half, pretty much. Okay, so this is one good approach to use. Okay, so or you can use you can distribute the CNN across multiple devices. This is, yeah, I mean, well, yeah, the TensorFlow allows you to train a model across multiple computers. We call that a cluster, okay? But this takes a lot of effort, okay? There's a chapter in the textbook that is dedicated to this, how you can train a model across multiple computers, okay, in a cluster, okay? I will not talk about that chapter, but you can check out the textbook for that, okay? So I think I'm done with the convolutional layer today. Okay, next week we are going to talk about pooling layer. Okay, that's the second important component, building blocks in CNN. Okay, yeah, thank you. Oh, by the way, not next week, the week after next, because next week is the field day, right? Field day.